Howdy, folks. Good to see you all again. All righty, so today we're going to be talking about graphs of functions. So in looking at how they look, what they look like. So the first thing we're going to talk about is when to determine if a graph is increasing or decreasing. So in other words, increasing. When does a graph look like you're essentially climbing a mountain? So we always, just like when we read left to right. It's the same thing with a graph. When we graph, we read a graph from left to right. So imagine I'm a person. Oh, I have a little long body. Very stubby legs, apparently. I am the world's best artist. All right. So imagine I'm walking on a function, on a curve. If I'm going up a mountain, that would be me increasing. At some point in time, I'm going to turn on that mountain, and we could see that here, happens at the vertex. And instead of going up the mountain, then I'm going to start going down the mountain. So when I start going down the mountain, as I'm going left to right, that would be where I am decreasing. Now, the proper name for increasing and decreasing is actually the phrase increasing domain. And decreasing is actually the phrase decreasing domain. And if you remember, domain refers to all the x values. So let's maybe make a note of that somewhere. Domain, all the x values. So as we're going through here, we're talking about increasing domain and decreasing domain. In other words, what are all the x values when my graph increases, and what are all the x values when my graph decreases? So when we're looking at this here, we'd say the increasing domain is going to go from negative infinity, because that arrow means goes infinity, negative infinity to when the x value of my vertex. So this is that 0.23. Just for the fun of it, here is positive infinity. So I'm going to go from the x value, so from negative infinity to the x value of that turning point. The x value, which is, if you notice, is the top point of the graph. We call that the maximum point. So I'm going from negative infinity to 2. So that's why we say the increasing domain is from negative infinity to 2. Now notice, it's a parenthesis here. Because when x is exactly 2, that's when the graph changes from increasing to decreasing. All right? Some people will say that it's constant at x equals 2. I don't really like that idea. I know why people say that, because that's where it flattens out. But the reality we just need to remember is that it's a parenthesis here at 2, because it's increasing all the way up until I get to 2. It's just not increasing at 2. And likewise, for decreasing, notice that I'm going to go from 2 to positive infinity. And that would be decreasing. You can see it right over here as well. So I'm going to put decreasing from 2 to positive infinity. Your notes has that. I don't know why it's on the left side, but it is. So increasing from negative infinity to 2, decreasing from 2 to positive infinity. Okay, so that's increasing domain and decreasing domain. So notice we're only dealing with the x values. Increasing and decreasing is increasing domain, decreasing domain. So as we keep going on here, another one we have is what we call the constant domain. So now a constant domain, it's essentially where the graph flattens out. In other words, when it's a horizontal line. So this right here has a slope of 0. That's the constant domain, because there's an interval where the graph neither increases nor decreases. Notice on this one, it is brackets. The constant does have brackets from 1 to 4. So notice if I were to walk along the graph here from left to right, I would be going, my y values would be getting bigger. So this is technically, this would be a increasing portion of the graph. So if I wanted to, I could actually go further and say, okay, it's constant from 1 to 4, but it's increasing from negative infinity to 1. Remember, that's going to be a parenthesis, not a bracket. Likewise, if I would go left to right here, I'm up here at the end of the constant, and then I'm going to, as I go to the right, I'm going to be dropping down the graph. That would make this part of the graph decreasing. So I'd be decreasing from when x is 4 to when x is a positive infinity. So a graph at any given point in time is either increasing, decreasing, or constant. If there is a part of the graph that exists, it's either increasing, decreasing, or constant. But it's always this part right here. We always go left to right. Go from the left to the right. Okay. All right. So hopefully we've got a decent idea of what increasing, decreasing, and constant is. We're going to come back and we'll look at that more here in a second. The next part is what we call an even function and an odd function. Now, notice what happens here on an even function. Let's see if I can't highlight a little bit. Even function says if I change every x to negative x, they end up being the same thing. If that happens, it's even. So here's my f of x. So every place where I see an x, we change it to a negative x. So negative x squared. Notice how negative times a negative is still positive. If you look here, these were identical to each other. And since they're identical, that means that this function, x squared minus 5, would have been an even function. We also have something called an odd function. So the first thing you always check is, if I ever ask you to check if a function is even or odd, check even first. If it's even, can't be odd. If it's odd, can't be even. Now, if it's an odd function, notice when you plug your f of negative x in there, they're not the same thing. But if we plug in negative f of x, in other words, multiply the entire function by a -1, a negative value. If these two are the same thing, if f of negative x is equal to f negative f of x, if these are the same thing, then we say that the function is odd. So what we're going to do here for a second is we're going to spend a little time here for a second before we move on here and figure out, how do we algebraically determine if a function is even or if it is odd? So let's say I give you the function f of x is x to the 4th plus x squared. Would that be an even function, odd function, or neither even or odd? So even, odd, or neither. So here, the first thing we want to do is we're going to take our function, and in place of x, we're going to plug in negative x. So for every x, we're going to plug in negative x. So every x will become a negative x. And what do you know happens anytime you have an even exponent? What does it do to a negative number? So -1 times -1, that would be a positive 1. Every time you have an even exponent, a negative term becomes positive. Every time you have an odd exponent, a negative term becomes negative. Try it. Say you take -1 squared. That would be 1. Say you multiply it by another -1. Then it would be a -1. If we keep going here, what about like how about a -1 to the 4th? Notice, every time we have an even exponent, the negative number becomes positive. Every time we have a negative exponent, the negative number stays negative. So -x to the 4th, and since that's an even exponent, that would become a positive value. If I have an even exponent, that would also become a positive value. And if we stop and we look at this here, here was this f of x was x⁴ x squared. F of -x was x to the 4th plus x squared. Notice it's the same exact thing. F of x equals f of -x. So we could then write, since f of x equals f of -x, then, I'll write that here in a second, is an even function. I don't have a math type on it. I guess I can write it in here. By the way, it's much more fun to do math with sound effects. If you haven't gotten to that point yet, start doing some sound effects. I tell you what. All right, so it's an even function. Likewise, let's try this one here. Take a second. I want you guys to see if you can come up with this one. F of x equal, let's try, x to the 5th minus 2x cubed. Pause the video and see if you can actually figure that one out. X to the 5th minus 2x cubed. Is it even, odd, or neither? All right, here we go. I plug a negative x in there. I get negative x to the 5th minus 2 negative x to the 3rd. And remember what we said, odd exponents will turn the value to be odd, or to be negative. So that becomes a negative x to the 5th minus 2 times negative x cubed. That's a negative value still, so that'd be a negative x cubed. So that means f of negative x equals negative x to the fifth plus 2x to the third. So now we compare. Do we have, that was the original function. And here's what we got here. Notice, not the same. Positive x to the fifth, negative x to the fifth. Negative 2x cubed, positive 2x cubed, not the same. So it wasn't even. So now we check to see if it was odd. So we're still going to use this, but now I'm going to go and I'm going to multiply everything by negative f of x. So I'm going to multiply the entire thing by negative . So when we're multiplying by negative, realize what that really is. We're multiplying by a negative 1. So negative f of x is negative x to the fifth plus 2x cubed. So when we look at that, you can notice here that these are the exact same. Since they're the same, since f of negative x is equal to negative f of x, now I'm dealing with an odd function. Since f of negative x equals negative f of x, then f of x equals, I should probably drop that down, f of x equals x minus 2x is an odd function. All right, let's see here. Like that, that. So that makes that in x to the fifth. Oops, wrong color. Ah, well. That makes that an odd function. Now, if you notice in your notes, it has this little 3 dot symbol. That little 3 dot symbol, that's the word, that's the symbol for the word therefore. Okay. So don't let that kind of confuse you. If you'd rather use therefore instead of writing the word since, totally good with that. All right, that's actually the math. 3 dots is this mathematical symbol for therefore. Okay. Just in case you were curious what that means. So that means therefore. All right. By the way, notice something. On an look at the exponents. They're both even. Therefore, this was an even function. This function, both the exponents were odd. Therefore, it was an odd function. What do you think happens if we have one even exponent and one odd exponent? So what if I give you the function f of x equals x squared plus x? And remember, this is the same thing as x squared plus x to the first. Even though there's not an exponent of 1, that would be the first. What would happen on that one? Let's try. I plug a negative x in here. I'd get a negative x squared plus a negative x. That means that f of negative x is a positive x squared minus x. So here's our original function. Here was our f of negative x function. We compare them. They're not the same. So what happens if we make it negative f of x? So if we take our f of x function, we multiply the whole thing by the negative. When we do that, we have negative f of x equals negative x squared minus x. So compare that one. This one doesn't equal the first, doesn't equal the second. Notice, these two aren't equal, these two aren't equal. Therefore, this function right here, we would say is neither. It is neither even or odd. Since f of x does not equal, and I'll change that here in a second, and f of negative x does not equal negative f of x, then f of x equals x squared plus x is neither even or odd. It is neither an even nor odd. So let's make those negative, or not equal to, and that should have had a squared. Okay, so hopefully we have an idea of even and odd. Right? This does come into play on some trig functions in later on in the school year. It also will come into play in calculus as well. So we need to have a basic idea of what even and odd functions are. All right, let's get going here again. Let's move a little bit here. No, there we are. Okay. Now, the last thing that we need to deal with here before we start looking at some examples are relative maximums and relative minimums. So a relative maximum, that is the peak of a function. In other words, a relative max is the function at its top. So here's the top of it. That would be a relative max. Here's the top of it. That is a relative max. Notice how what the graph does. It goes up, increasing to decreasing. The graph changes from increasing to decreasing at a relative max. A relative min minima is the value of a function. So that's when it is at the very lowest. So here, right here, is a relative minimum. And so we write that as a point. Just for the fun of it, take a second. I want you to tell me when the graph is increasing and when the graph is decreasing. So I want you to tell me when the graph is increasing and when the graph is decreasing. Go ahead and pause the video and do that. Right, so here we go. This is the graph increasing here and decreasing here. From here it is increasing. And here it is decreasing. Notice the relative maximums always exist when the graph goes from increasing to decreasing, increasing to decreasing. Relative minimum is when it goes from decreasing to increasing. So if I want to go ahead and write my values here, Remember that I'm only dealing with just the x values. I don't care about anything else. All I care about is the x values. So for this right here, increasing, I'm increasing from negative infinity to -6. Then I was decreasing from -6 to -3. And then increasing from -3 to 0. And decreasing from 0 to infinity. And we got it. All right, so we got relative min, relative max. Some relative maximums, they're peaks of mountains. Relative mins, they are the valley, the lowest of the lows. And that brings us to our last part. We're going to be able to go through and do the entire thing. Now, these graphs right here, I'm going to have to give you the graph. Eventually, you guys will know how to come up with the graph. And in the second chapter, Ms. Hodge is going to teach you guys how to use your graphing calculators to be able to figure out where all these points are on your calculator. But for the time being, I'm going to have to help you guys out here a little bit. So let's see here. We're going to have this right here is the point, -1.6 and 13.9. Now, actually, I should probably do this correctly. 385 and 13.8565. Just so you're aware, friends, in pre-cal and calc, and you should have done the same thing in integrated 3, I believe. We always want to go out to 3 decimal places. I recommend 4, because if you go 4, then you don't have to worry about counting ever, or rounding. If you go 3, the College Board and Calculus and AP Stats will make you round correctly. If you go 4, they just pretend you know how to round and they don't ever dock you. All right. So we have ourselves a couple points here. Let me draw this out here. And we're going to make this graph go like this, and up like that, and like that. Wasn't the best looking graph, but hopefully you can kind of tell. So at this point right here where it turns is here, and this point right here where it turns is that. All right. So the first thing we want to do, we want to know when is it decreasing, increasing, and continuous. Well, there are no continuous domains, so we don't have to worry about that. There are no flat sections. So we can go ahead and just skip the flat section. But increasing, decreasing, and constant. So for the constant, we're going to say that this is DNE. That's short for does not exist. Increasing, that's when it goes up. So here we go. I'm going up, so that makes this increasing. I'm going down, that makes this decreasing, and up again, that makes this increasing. So again, remember on these, we only care about the x value. So I'm going to deal with just the x values. Okay. So let's see here. Increasing from negative infinity to negative 1.6385. and decreasing from negative 1.6835. Remember, for my increasing and decreasing, I'm using parentheses for the entire thing. 2.3052. And these are parentheses. But I got another increasing domain, so I'm going to go ahead and write the word and. Zero. 5, 2, to infinity and beyond. That never gets old. It probably gets old, actually. All right, so domain range. All right, well, I got my increasing, decreasing constants. So I did those already. I did forget to do my domain and range, so let's go ahead and deal with that. Notice, my domain is always going to go from my smallest value to my largest value. So I'm going from negative infinity to infinity. So my domain is going to be all real numbers. So that'd be all real numbers. Notice my range. Now, range is when I'm dealing with the y values. So I'm going from negative infinity up to positive infinity. So my range is also going to be all real numbers. Did domain and range now? Even, odd, and neither. So even, odd, and neither. That means the whole, if it does f of x equal to f of negative x. So if I were to plug negative in for all those x's, you guys know how to do that now. So I'm going to kind of abbreviate this here a little bit. So here's what f of negative x is. Odd exponents, the sign changes. Even exponents, they don't. So f of x does not equal f of negative x. And let's go ahead and do the negative f of x now. So this isn't even. I can already tell it's not even. Is it odd? Hopefully you guys know the shortcut here. You should be able to tell just by looking at it, since I have both even and odd exponents, that this is actually neither. But we have to show it algebraically. Since f of x doesn't equal f of negative x, and this doesn't equal these two, so we are going to go ahead and just say that this is indeed neither. Now, we'd want to write our statement like we did before, but I'm running out of room. And last and certainly least, our domain and range, or I'm sorry, our relative min and relative, the extrema. That's our relative min and relative max. So here's our extrema. That just means relative min and relative max. So my relative minimum is this value right here. So extrema means relative min, relative max. So here's my relative minimum. So I would write it as a point. And then I'm going to have my relative max. My relative max is going to be this point right here. Well, friends, let's have you guys go ahead and try one, because I think that'd be fun and exciting. All right, let's see here. Let me draw this up here for you. And, okay. This one's going to have an x-intercept at -3, an x-intercept at 1, an x-intercept at 0. It's going to have a point up here as well. Let me tell you the coordinates for that point too. Let's make this point right here, ooh, -1.6667, 9.4815. Go. That'll be that point, and the graph's going to look like this. I just realized. Kind of forgot. Parentheses. All right. And we'll draw this out here. So we're going to make the graph look like this, come down, turn in there, come in here, and oopsie daisy, like that. All right, friends. Do the same thing. Domain range, increasing, decreasing, continuous, even, odd, neither, and extrema. Go and pause video, take a second and do it. All right. I'm sure you all paused the video. Here we go. Domain. Just like before, domain is going to be all real numbers. Range, also going to be all real numbers. Now notice here, I didn't give you all the points. We need this point. So let's write it in there. It's 0.10. So now I can do my increasing, decreasing, and constant values. So all we care about these ones again are the x values. All right. -infinity to -1.6667. Decreasing from -1.6667 to 1, and increasing again from 1 to infinity. Constant, there was none, so we just skipped that part in general. D, N, E was no constant. All righty. Relative max and relative, no, got to go do the neither part first. And I'm not going to go through and do this whole thing again. You plug in your, you can tell right now at the very beginning it's going to be neither, just because the exponents are both odd and even. But you would have to prove that algebraically like we did before. And negative here. And again, since none of the three are the same, that makes it neither. And then lastly, our extrema, in other words, our relative min and max. That is -1.667, 9.4815, and our relative minimum. That's just the point, 10. Good so far, hopefully. All righty. Let's move one more space here. Now, before we get to this guy, we got to have a real quick debrief on what the stink is a piecewise function, because these are dealing with piecewise functions. So I'm going to add one in. We need to first be able to graph a piecewise function. Piecewise function means basically that it is pieces. And x minus 2. So when you're dealing with these, the first thing you want to look at here is that these are two different functions. So our first function we have here is the function y equals x minus 1 squared. So our h value is 1, our k value is 0. So if I were to go through and graph this one real quickly, it looks something kind of like this. The vertex would be here at negative 1, 0, and it would go up like this. So there we are. And then the second function, x minus 2, so that'd be like y equals x minus 2. So you got to remember on piecewise functions, and again, you did a little bit of these back in integrated 3. On piecewise functions, you had to first figure out where the graph was, where the y-intercept is, and then you did your slope from there. So you go, all right, well, let's go this way and make my slope positive 1. And there we go, something like that. Now, what a piecewise function says is I only want to deal with just individual pieces of this. In other words, I only want to deal when x is less than 0. So we want to treat this like an inequality. So an inequality, x is less than 0. If you see less than or greater than, that's one type of dot. If you see less than or equal to or greater than or equal to, that's a different type of dot. And remember that less than or greater than, that's an open dot. Less than or equal to or greater than or equal to, that's going to be a closed dot. So this says I'm going to be dealing with x is less than 0. So we're going to go to our graph and figure out when x is less than 0. That would be right here at the point 0, 1. So that's an open dot. And it says I only want the part of the graph that's to the left of my function. I only want the x values that are less than 0. So would that be the right side of the function or the left side of the function? Hopefully you guys can tell me. That would be the left side of the function. So when I go to make my graph, I only wanted just the left side of the function. I wanted this side right here. So when I go to make my graph here, I'm going to have an open dot at 1, and then I want the left side of the function. So that would be coming over here as a curve. Likewise, when I do my green part here, when I do the green function, it said x is greater than. Let me make that greater than or equal to real quick. That means when x equals 0, so here's 0, greater than or equal to, that's a closed dot. And I want all the x's that are to the right of the function. So that would be all the x's that are greater than. So that would be this side of the function. So let's go ahead and add our green function on here. So x is greater x minus 2. Then I have a slope of positive 1. So it'd be looking like this. So that's a piecewise function. So this right here is the graph of this piecewise function. So when I'm looking at my graph here, I got to do all 3 different portions. So notice this one has 3 different things. It has f of x equals x plus 6. So it's going to be dealing with y equals x plus 6. So that'll be this part right here. It's going to be dealing with y equals 3. And it's going to be dealing with y equals x minus 3 squared. So for this, if we're dealing with the graph, let me just make a real quick outline of what these graphs are going to look like, so that way we know when we put the pieces together what we're actually seeing here. When I do the line y equals x plus 6, that's going to be looking like up here. Y equals 3, that's this kind of a graph, a constant graph. And x minus 3 squared, that's going to have a vertex at 3, 0. So that's going to be looking like this. So we're going to have to put all these pieces together. Oopsies. That was a little cockeyed. There we go. All right. So our first graph says y equals x plus 6. We want to do this when x is less than negative 3. So less than negative 3. So negative 3 will be about here. And I'm dealing with the graph that goes below it. Okay. So to the left of our x value. So let me graph that here. Right. One way to do it, probably one of my favorite things to do on these, is I usually take this end value right here. I call that kind of like the starting point. I just plug it in. So if I plug negative 3 in here, negative 3 plus 6, that's 3. When x is negative 3, that's a positive 3. That's a real easy way to do it. If you have these boundary points, just plug them in. And now pick a number to the left of it, like negative 4, and that would be 2. So that means this graph is going to be going down this way. Y equals 3. Notice it's going to have a solid dot here at negative 3. So it's going to have a solid dot at negative 3. And it's going to have an open dot at positive 1. And we want all the stuff that is in between. Since x is between, we want everything in between. So when we look at this here, then notice there's an open dot here from the last part of the graph. Well, my closed dot will fill in my open dot. And then I'm going to have an open dot over here at 3. And then we're going to tie them together. So this is, spend a little more time on piecewise functions. In the past, we did algebra second semester. So the piecewise functions had a separate day. So you guys already knew how to graph these ahead of time. Notice on this one, oh, I just realized there was a -1 there. Oopsies. So let me see here if I can fix that a little bit. There we go. Notice that it has the vertex at 3, -1. So let's go ahead and put our vertex there at 3, -1. And it says I'm going to go from x is greater than or equal to 1. So that would be right about here somewhere. And I want everything to the right of it. And I'm going to play the boundary. I'm going to do the boundary point thing again by taking my 1 and I'm going to plug it into my function here. So if I plug 1 in here, 1 minus 3 is -2, squared is 4, minus 1 is 3. So that it'd be at 1, 3. And again, that's the same point where this was already open. So I'm going to close it down and I'm going to draw a parabola that will connect them. All right. Even, odd, neither. Friends, this is going to be a neither function. Don't even worry about it. This is neither even or odd. I don't want you to try to mess with cleaning this one up. But why don't you take a second there, tell me the domain, the range, increasing, decreasing, constant, relative max, relative min. All right, go for it. All right, domain, notice, has every real number known to mankind. So therefore, our domain is all real numbers. Range, arrow going down here, arrow going up here, it's all real numbers. Increasing, well, let's see if we can't go through and just mark off all the pieces here. So this is an increasing part here. I have a constant here. I have a decreasing here. And I have increasing here. So increasing goes from -infinity to -3. It's a parenthesis. And I also had increasing at the end there from +3 to infinity. Decreasing is this little part right there. So I'm decreasing from 1 to 3. Notice this time we do have a constant value. So constants, they're going to get the bracket. So I'm constant from -3 to 1. Relative max. Do I have a top of the mountain? Notice there isn't any top of the mountain here. This is a plateau. So there are no tops of mountains. So I don't have a relative max. So we're going to put D and E on that. But relative min, do I have a bottom of a valley somewhere? In this case, I do. The bottom of the valley is at 3, -1. All right, you guys were good sports. This was a really long lesson. All right, so nice job. Way to stick with, and I will talk to you guys later.